All right, let's talk about the backbone of pretty much everything we do with data, the data pipeline. For years, these things have been the unsung heroes, right? Moving and transforming all our data. But let's be honest, they've also been incredibly fragile. Well, that's all changing. A massive transformation is happening right now, powered by AI, and it's promising to turn these brittle workflows into smart, autonomous systems. So let's just start with the question that I know keeps data engineers everywhere up at night. Why do these things break all the time? Seriously, it's a pain we've all felt. A critical report fails, a machine learning model doesn't get trained, and suddenly everyone's scrambling. To really get why the future is so exciting, we first have to understand why the past has been, well, so painful. And that takes us right here, to the old way of doing things. For the longest time, data automation ran on a super simple, decades-old tool that, frankly, was never built for the kind of complexity we have today. It was basically a ticking time bomb sitting at the very heart of the data stack. And that tool was cron. The best way to think about it is as a blind scheduler. It's fantastic at one thing, running a script at a specific time. That's it. It has zero awareness of anything else. No dependency management. That means it'll just happily run a job even if the step before it failed, leading to totally corrupted data. And it fails silently. So a critical job could be broken for days before anyone even notices. It also causes this thundering herd problem, when everyone schedules their jobs for midnight and the whole system just crashes. And finally, it's completely static. It only understands the clock. It can't react to anything. So all these constant failures with cron, they really forced an evolution. Data engineering had to grow up. It had to start borrowing principles from software engineering to bring some order to all that chaos. And this was the first huge leap forward in what we call data orchestration. And that revolution came in the form of the DAG, the Directed Acyclic Graph. Suddenly, with tools like Apache Airflow, engineers could define their pipelines as code. Each little task is a node, and the arrows between them show the dependencies. It sounds simple, but it was absolutely profound. For the first time, you could guarantee that task B would only run if task A actually succeeded. This one idea prevented just countless cascading failures. It was a game changer. But, the evolution didn't stop there. The focus started to shift. Instead of just caring about whether a task ran or failed, platforms like Dagster started asking a new, much more important question. What about the data itself? This is the move from thinking about tasks to thinking about assets. The main concern is no longer just, hey, did the script run? It's now, is my sales report up to date? And did it pass all the quality checks? This lines up the tech directly with the business value it's supposed to be creating. Which brings us to today, and the next massive paradigm shift. We're moving beyond systems that just react to things that have already happened. We're moving to systems that are proactive, systems that can actually predict and act on the future. This is the AI frontier. This timeline really puts it all into perspective, right? We started in the past with cron, totally static, purely time-based. Then we moved into the present with DAGs, which are reactive. They respond to things like a task finishing. And now we are stepping into the future, proactive, predictive orchestration, where the system actually anticipates what's needed before we even know we need it. Okay, let's dive into this table for a sec because it makes the difference incredibly clear. Just look at resource allocation. Cron, static, and manual. DAG-based systems, mostly static. But AI-optimized systems, we're talking dynamic, predictive auto-scaling. They don't just react to a spike in demand. They add resources before the spike even happens. Or check out fault tolerance. We go from manually rerunning jobs with cron to automated retries with DAGs to true self-healing with AI. It's just a massive, massive leap in intelligence. So what does it really mean for an orchestrator to be intelligent? Well, it really boils down to these 4 core principles. You've got autonomy, so it can act without a human stepping in. Adaptability, so it can react to changing conditions on the fly. Efficiency, to optimize for cost and speed. And maybe the most important one, SLA-driven prioritization. This means the system actually understands the business goals and will prioritize jobs to make sure the most critical data gets there on time. Now, this all sounds great in theory, but how does it actually work under the hood? This AI grain isn't some magic black box. It's actually a really clever architecture built on 2 powerful, connected pieces, the ability to see the future and a team of digital workers to act on that vision. The first piece is workload forecasting. It's pretty cool. The system just analyzes all the historical logs, how long jobs took, how much data they processed, the resources they used, and it uses all that data to build a model that can predict those same things for future runs. It's all about knowing with a pretty high degree of confidence that tomorrow's big job is going to need a certain amount of memory and will probably take about 45 minutes to run. Now, what's really interesting here is that there's no single best way to do this forecasting. The right model really depends on the personality of the job itself. So for a really stable, predictable job, a classic model like ARIMA is perfect. For a job that's tied to the business calendar, like a weekly sales report, Meta's profit model is fantastic because it gets seasonality. And for those super complex volatile workloads, you'd want a deep learning model like an LSTM. So once you have all these predictions about the future, who or what acts on them? This brings us to the second component, multi-agent systems. And honestly, the best way to think about this whole thing is as a digital twin of a really high-performing data engineering team. And this slide just illustrates the concept brilliantly. Instead of one giant monolithic AI, you have a team of specialized software agents. The forecaster is like your capacity planner, predicting what you'll need. The scheduler is the project manager, mapping out the best way to hit all the deadlines. The resource allocator is the platform engineer, spinning up all the infrastructure. The monitor is your SRE, just watching everything in real time. And the recovery agent, that's your on-call engineer, automatically fixing things when they break. Okay, so let's move from theory to reality. How are these concepts actually showing up in the tools and platforms that we use every day? And even more, what can we learn from the huge companies that have been operating at massive scale for years? Well, when you look at the major cloud platforms, you start to see two really distinct philosophies emerge. On one side, you've got Databricks, which acts more like an intelligent actor. Its features make a lot of the optimization decisions for you. It's a very managed experience. Then, on the other side, you have Snowflake, which is more like a powerful toolkit. It gives expert teams all the building blocks they need to build their own intelligence systems, which offers a lot more control. So, those are the platforms you can buy into. But where did these ideas even come from? Well, they were really forged in the fires of hyperscale. The big tech companies have been solving these problems for years, just out of sheer necessity, and their lessons are so valuable. Netflix, for example, is all about incremental processing. Only touch the data that's actually changed. Uber learned that deep observability is the only way to control costs at that exabyte scale. Airbnb saw huge resource savings by letting Spark's adaptive query execution tune jobs on the fly. And Spotify showed the power of doing work early, pre-computing things to avoid expensive work later. And if you boil all those lessons down from all those leaders, there's one crucial point that emerges. It's this strategic shift. They're all moving computational work from runtime, when a user is sitting there waiting for a query, to write time, when the data is first being created. It's just so much more efficient to invest a little compute power upfront to organize and optimize your data because it saves an enormous amount of cost and time later on. But this new world of autonomous, predictive pipelines, it isn't perfect. It's not without its own challenges. In fact, it introduces a really subtle but profound new kind of risk that we never really had to worry about with the simpler systems of the past. It's called prediction-induced failure. And this is where your pipeline can fail even when every single component is working perfectly. How is that possible? Well, if the forecasting model gets it wrong, say it predicts low demand right before a massive unexpected spike, the system will flawlessly execute that bad advice. It'll scale down resources and cause a catastrophic failure. Suddenly, the reliability of your entire platform is directly tied to the accuracy of its own internal ML models. Which leaves us with this final provocative question. Is your next data engineer an algorithm? Now, the answer isn't a simple yes or no. The role itself is what's changing, fundamentally. For the hands-on engineer, it means you'll shift from manually tuning jobs to designing and supervising these autonomous systems. For managers, it means rethinking your team's skills, prioritizing people who can reason about these complex AI-driven platforms. And for everyone in data, it means learning to trust, but also verify, the decisions made by these intelligent agents. The future isn't about replacing humans. It's about augmenting us, shifting our focus from being the mechanics to becoming the architects of these incredibly powerful new data ecosystems.